Welcome to Next in Tech, an S&P Global Market Intelligence podcast where the world of emerging tech lives. I'm your host, Eric Hanselman, Chief Analyst for Technology, Media, and Telecom at S&P Global Market Intelligence. And today, we're going to be talking about chiplets, an interesting advance in semiconductor manufacturing. And with me to discuss it is John Abbott. John, welcome back to the podcast.
Hi, Eric. Thanks for inviting me.
And thanks for being back. There seems to have been a lot in the news recently about what is a new set of technology advances in semiconductors. And I guess something that actually hasn't been brand new, but certainly is seeing a lot more use and utilization in designs recently. I guess it's a technology that we've seen for a while, but the idea of being able to go build devices from a number of small pieces of silicon, linking them together, binding them actually on a substrate at a relatively small level, something called chiplets, basically small chips working together to be able to package it. This is something that I guess it's been out in the market for years, but suddenly seems to have gained prominence.
Yeah, really interesting, I think. And I should point out that Intel sometimes uses the term tiles, which means maybe something slightly different, but it's the same idea. And I suppose with Moore's law generally agreed to be near the end of its life, things had to change. We've seen lots of more cores in processors in general for many years now. But it was really the development of these massive dies and the huge amount of errors that would come about during their manufacture that sort of forced Intel and AMD and the other chip companies to think about a new approach where they could modularize the whole process. Yeah, I think the whole thing came out of the development of SoCs, which has got a UK context, which is pretty interesting for me. I think the first SoC system on chips were built for, I think, your watches and things in the 1970s. But I think the first significant SoC was the ARM 250, which was made by a company then called Acorn, from which ARM, the chip company, was eventually spun out from. And the ARM 250 combined 4 discrete chips, which was memory controller, video controller, I/O controller, and the compute element. And that was used in Acorn desktop PCs, but it was also licensed widely to set-top box manufacturers and other embedded devices. And from that, I think, evolved the ARM SoC, which ended up in smartphones and tablets. So quite a legacy, really.
Oh, wow. All right. We're going way, way back. Well, but you point out what is that interesting transition, which is that the idea is that you can take functional blocks, because originally a lot of big integrated circuits got designed. Really, each individual one was designed specifically for its particular function. But when you start thinking about systems on chip, what you start to do was to take a functional block, like a processor, like a memory controller, like chunks of memory.
Yeah.
That each one of them would have their square space on what was the final finished die, but that it was one single piece of silicon, granted very small, we're talking millimeters on a side until we started getting into much larger processors. But the idea was you'd put them all on one single piece of silicon. You'd have hundreds or thousands of them on a single silicon wafer. But that point that you made is that the more area that starts to occupy, the greater the chance there is for some kind of manufacturing error to take place. And the bigger you make the die, the larger the area, and the greater the potential for an error to creep in the manufacturing process, a defect, metal lines that don't work out, some of the doping process that didn't work properly, what have you. And we've been dealing with getting manufacturing better to be able to make those devices larger and larger and larger, and especially when you start thinking about large microprocessors. Now you're starting to get into die sizes that are really pretty significant. And the challenge then is that making them at high enough yields so that most of the ones that you make are actually successful functional devices gets harder and harder.
Yeah, so I think Chiplets takes the whole idea of SoCs to, which was essentially still monolithic, as you say, to a whole new level where you create these multi-chip modules, you connect up dies of different styles, different process technologies as modular building blocks like Lego that let designers build out a complex chip made out of highly specialized modules and connected to each other through these new sort of package level integrations. And I think the detailed work on that began at DARPA sometimes in the mid 2000s with the CHIPS project. And that was really where some of the basic work was done. I mean, there's some really interesting reasons, I think, for doing this. One is, as you say, to get around the increasingly hard task of building huge monolithic chips and keeping the defect rates under control and getting good enough yields when they're manufactured to pay back all that massive investment as well. So it potentially, the whole large chiplets idea potentially lowers the barrier of entry into the semiconductor market to smaller companies and startups that can just concentrate on the bit that they really want to develop with their core area of expertise. And ultimately, if chiplets can be sourced from multiple suppliers and made to work together and standardized, they can be used as mix and match components. And then we might see like highly optimized, purpose-built modules for very specific tasks, something that's really hard, too expensive really to do now. And I think we've seen an example of that in the AI accelerator startups that all started to emerge around 2015. And they each built their AI accelerators for what they saw the problem was going to be in AI when they came out 3 or 4 years later. And then in 2017, Google came up with the transformer model, which they hadn't really anticipated. And obviously last year, was it? That exploded into generative AI and all these.
All right, now you've said it. Oh, we've gotten into AI.
So all those chip companies that had done their designs did it before they knew what really the problem was. And so chiplets could help solve that by making it much quicker to get to market with silicon for specific problems. And also, this eventually should be a lower cost way of doing this, end up with more energy efficient systems as well, with any luck. So it's pretty interesting.
Well, but it's not as simple as it sounds, right? I mean, it's something where the idea that, oh, all right, you just simply take small functional blocks and stick them together and life is good and off you go. It is, in fact, a lot more complex. And if we think about it, semiconductor manufacturing has been taking multiple dies of silicon and packaging them together. But the early attempts were all, you'd go to the substrate of the lead frame, basically the metal frame or the ceramic frame that actually sits inside what eventually is the plastic encapsulation.
Yeah.
And you actually run small gold wires back and forth between them. Yeah. Those early efforts, you could get multiple devices. This was something people did to build high density memory packaging and things like that. But of course, that's kind of fragile. Getting all the wires interconnected is difficult. It's complex. There's an additional manufacturing step. What we're talking about here is actually something that is bringing these devices together in a much more tightly integrated way.
Yeah.
Because we've done things like being able to take, in a lot of mixed mode packaging, you want to have something like a laser, and you actually have different process types that you're trying to bring together. And so you take a small laser, and you effectively glue it eutectically down onto the regular CMOS thing, that's the device that's sitting below it. Yeah. This is doing this at a much different scale and tackling what are a whole bunch of really complicated problems, especially when we talk about any of these high performance devices that throw off a lot of heat. You've got to figure out how to manage the heat. You got to do the interconnect. This is not just simply sort of stack them up and off you go.
No, that's true. And you can see that by what TSMC has been working on recently. They've shifted their R&D over the development of advanced packaging, things like SOIC, System on Integrated Chips, 3D Fabric, and CoWoS, which is chip on wafer on substrate, which is one of the things that NVIDIA has had trouble with in getting GPU availability up to its thing. So these are really advanced packaging techniques. And it's interesting to see what AMD and Intel have done to get some of this stuff to market, at least in a proprietary form, sort of under the covers, really, as part of their product. So AMD has been using chiplets for its EPYC processors, and its chiplets are separate dies mounted on the PCB substrate, and they're connected through the substrate using a sort of SerDes serializer and deserializer, basically turning what would have been a parallel bus into a serial bus to connect up these modules. So each connection, that does add some overhead, power, latency, and bandwidth overhead, but it allows you to scale up to many more modules. And it's basically a relatively easy and cheap way of doing this. If you look at what Intel's done, they've spent the last 15 years working on this advanced packaging stuff like EMIB, which is embedded multi-die interconnect bridge, and Foveros, which is 3D stacking of putting silicon layers on top of each other. And so they use that EMIB bridge as an interposer, a separate piece of silicon that links the two chip modules together. And that also embedded more tightly into the substrate than traditional older sort of interposers. So that's a more expensive approach. And it's taken, as I said, decades of development to get there, but it's more efficient. It's got less performance overhead, and probably it's more reliable in things like data transfers. But the AMD approach allows you to spread out your chip modules a bit more, and that might be useful in some respects if you've got very high heat density and stuff like that. So there's a lot of core challenges to this, and one of those is getting that advanced packaging so it's reliable and cheap enough and easy enough to manufacture at volume. And as I said, the shortage of GPUs is partly due to that. Then it's things like testing the multiple chiplets on a single package, how you do that. Then it's about the complexity and the efficiency of those interconnects and how they're designed and integrated. Things like thermal design, heat density issues. And then there's another one, security and trust. Can you trust chiplets that might be designed by third parties? Verification, certification, and trusted supply chain. Chiplets from one source will have to be guaranteed to interoperate with chiplets from something else. And of course, that's when we get to a standardization thing. At the minute, Intel and AMD are doing this under the covers using their own technologies. It's not standardized. It's, in the future, we may see a full ecosystem evolving around chiplets, which I think is when it becomes really interesting.
Well, and all those issues of interchange. I mean, let's start with just simply the interconnection, because there is that challenge. Are you trying to make the interconnection simple or fully functional? I mean, if you were building a system on a chip or a system on an IC, you'd actually wind up having lots of parallel interfaces that were actually on that same die.
Yeah.
And the big advantage is that you don't have to get to the levels of either higher voltage or higher current to be able to go drive those interconnects. But when you have to get from one chip to another, now you've got to figure out how do you go manage what that interconnection is, because you've now got to have robust enough communications. And serial communications wind up being really easy. You only have a single path that you have to go between die to die. But as you're saying, you've got to get the serializer, deserializer. You've got to get something that takes the parallel interface and converts it into that single interface. The other side of that coin is that if you want to do parallel interconnects, do something like Intel's been doing with some of their interposers. You actually have a layer that's kind of like a little silicon circuit board in between these two devices to be able to have lots of parallel interconnections. Now you've got to make sure that all of those parallel connections are actually functional.
Yep.
And you've got the manufacturing challenge of not making sure that just one connection works well, but all of your parallel connections are appropriately set up. Yeah.
Absolutely. Yeah. It's a complicated thing. And a lot of those things haven't really surfaced in real products yet, so we don't really know how they'll play out completely. But I mean, the standardization process is quite interesting as well, because it's got to encompass all those various layers. So the Open Compute Project, for instance, has been collaborating with standards bodies like JDEC on low-level chiplet design exchange, CDX they call it. It's sort of seeking to establish standardized chiplet models for the development and validation of chiplet designs. The idea is really to get the basis in place for an ecosystem of the various types of companies that would need to be involved. Things like people like EDA companies like Cadence and Mentor and what's the other one?
Oh,
Synopsys.
Synopsys. Yep. All those guys.
Yep.
Yep.
The silicon IP providers, the outsourced semiconductor assembly and test companies that put some of these things together, the chip fab operators like TSMC and Samsung, and the material suppliers and stuff like that. All those people need to be involved. And so the standard, we've had some low level standards for a while, like the bunch of wires open source specs that OCP is backing, the physical layer. And some of those have to encompass some of the older physical layer standards, like ARM's Amber standards, for instance, have been around for a long time to connect SoCs up. So there's still a legacy there. And then there's these higher levels, and that's addressed by things like UCIe, which is the Universal Chiplet Interconnect Express, which is an open spec for die-to-die interconnect and serial bus between chiplets, which has got a lot of backing from ARM, AMD, Intel, Meta, Qualcomm, Samsung, and TSMC are the sort of biggest backers. There's plenty more. But that is a sort of much higher level. It tries to encompass all the major packaging technologies, things we've talked about, silicon imposer on bridge, RDL fan-out, organic substrate or laminate, all that. But also the higher level things that are also emerging, things like PCI as it actually is now, and CXL, which is how you connect up different accelerators and CPUs and GPUs at a much higher level at the PCIe bus standard. So it's trying to do all these things. It's trying to be, as it says in the tin, universal. And that may be something that's quite hard to actually get to.
One standard to rule them all.
Yeah, with so much baggage that it becomes almost impossible to use. But we'll see. It's a good ambition to have. And the OCP is working particularly hard, as I said, to try and get some of these low-level companies together to form the basis of an ecosystem. And then you could source some of these chiplets from multiple sources. And that's when the model would really start making sense. A bit like software modularity, standard software libraries that we've seen for years now.
Well, I'm fond of talking about the power of abstraction in technology, but this is really standing that whole shift on its head, because we're going from JEDEC standards that are really talking about macro packaging things. Where are the pins? Where are the pads? What's the dimension of the ball grid array in terms of where it will fit on the printed circuit board? All those kinds of things. This is now driving inside into the die and trying to do that same kind of standardization, getting into the inside of the chip design itself. So really working from what was the macro into the micro, or I guess if we're heading down that way, nano kind of level, to be able to specify some of the internal standards in a place in which this has always been the realm of the internal proprietary interconnections that the chip designers themselves have put together, are now they're trying to put standards into this in ways that these are internal pathways that have always been really highly optimized. Yeah. Because you're looking for performance, you're looking to optimize thermal characteristics, you're doing some basic silicon design things here. Yeah, now we're trying to lay a standards umbrella across, and that is not a simple process.
Absolutely. But if they can get there, some of the new open hardware initiatives, like particularly RISC-V, are now coming up with very focused bits of silicon IP with low royalty rates potentially as well, and fast to market. And it just would make sense if they can plug those in to different architectures. I think there'll always be very proprietary approaches to this that won't, that Intel and AMD will keep their secret sauce to get as much performance and product variety as they can do themselves. But above that, we might see for some more standardized functions, the ability to slot in a piece of RISC-V technology, for instance. And where it might make also more sense is in those specialized chips that you see from, running at the edge or in industrial equipment from the likes of TI, NXP, ST Micro, where they want to embed, for instance, intelligence, AI intelligence, for instance, at the edge. And they haven't been able to really yet because of the cost constraints and sometimes the power constraints as well. So hopefully the enough standardization efforts will be realized so that you could do that into the intelligent edge, for instance. I see that's a really interesting way of doing it. And to use things like RISC-V to get to market quicker with more specific, accelerators.
Well, you point out RISC-V, because here you've got what is a packaged processor design, and you've got something that is going to have you have a design for the processor itself that has, is already laid out a particular way. If you can integrate into that the ability to have interconnects that could provide chiplet connectivity, now you've got what is relatively low cost. This is the same kind of templating that we've seen with other silicon optimized processors like ARM, who were able to put these things together. I thought it was interesting. MediaTek announced their partnership with NVIDIA, and you were talking about being able to get AI processing at the edge. Maybe these are the kind of things that they can use to be able to create devices that have the power efficiency of being integrated at low level, that they've got the ability, you don't have to go off chip. So I think that's implicit in all this is anytime you have to go off chip, you have to bump the voltage level up to be able to get strong enough signals to go chip to chip on a circuit board. If you can do that integration die to die within the package, you keep the voltage levels lower, you keep the power consumption lower. I did think it was interesting that as part of that MediaTek NVIDIA announcement, they mentioned that they're going to use NVLink, which is NVIDIA's standard interconnect for the GPU, not a specialized connection, but one that is actually the standard external connection for GPUs.
Yep. And that's another bit of a lock-in as well, in a way, because NVLink is NVIDIA specific, but it's very high performance as far as it goes for the connecting up those things. And I think, we'll see more activity there as these hybrid chips, CPU and GPU, like NVIDIA's Grace Hopper, come out, and AMD's equivalents as well, where they integrate the CPU and GPU and potentially DPU as well into a sort of super chip. So I think there's quite a lot of interest there. I think MediaTek is interesting because they've got such an established user base of things like video processing and things like that. So this is obviously potentially good for them in integrating with established GPU companies like NVIDIA and AMD. So I think that's certainly very interesting.
And you mentioned also AMD. I think it's interesting to note that AMD actually has been touting the fact that its new, what it sees as its big competitive GPU, is in fact a chiplet-based design, the MX300, that they're identifying up front that it was built from chiplets so that they could optimize the processing pieces, the GPU pieces, the memory pieces, and combine them all together into one more cohesive and potentially more powerful whole.
Yeah, and I think that's, as we're recording this today anyway, I think AMD is actually launching that chip today. And next week, I think Intel is launching, I think it's Meteor Lake, isn't it? Their mobile processor, which also uses chiplets. So we're seeing this coming into the mainstream products.
Well, because I think as we've been talking, it's for so long, the actual build of a semiconductor device was expected to be one unitary whole. You had fabrication process nodes. You were going to be building this piece of silicon with this particular process, and You had memory processes that were optimized for the memory structures. You had processors that were optimized for density and ensuring that you'd get the kind of granularity that you were looking for. Now you've got the ability to mix and match process nodes so that you can get memory that's been built in an optimized environment. You can get processors or GPUs or other ancillary devices that were built in their optimized nodes and bring them all together.
Yeah. And,
hopefully with standards.
Yeah, absolutely. And you can see how that could really benefit. For instance, GPUs are often constrained by the amount of memory that they have access to. And you could see more variants of greater types of memory onto GPUs, which would be of great benefit, I think, in the future. And you look at what AMD's done with EPYC, if they've sectionalized it off into HPC, more standard CPU, telco variants of EPYC using this concept.
Well, it's certainly, it opens the doors to a whole set of potential new capabilities. Still clearly some things to overcome in terms of standardizing not only the reliability, the design, the kinds of the ways in which you can actually leverage them. But I guess there is much more to come, but we're certainly on an interesting cusp in terms of where this transition sits today.
Yeah, I think if and when the standardization process comes along, and I think it will, I think it's inevitable, really, that's when it becomes interesting. It's really early days yet. But once a third-party system ecosystem becomes involved, then we could see more specialized devices, more affordable, maybe opening up new types of advanced devices to less developed economies, and also lower costs and lower power consumption at the edge, particularly for AI inference, which is going to be a massive deal over the next couple of years.
Well, a lot of opportunity. I guess we'll have to see where that turns out. Well,
yep.
This has been great, John. There are so many other things potentially to explore, but we are at time for today. Okay. Thanks for all the perspectives.
Lovely. Thanks, Eric. Enjoyed it very much.
And that is it for this episode of Next in Tech. Thanks to our audience for staying with us. And thanks to our production team, including Carolyn Wright and Caitlin Buckley on the marketing and events teams, and our agency partner, the 199. I hope you'll join us for our next episode, where we're going to be talking a little further about what was happening at the Open Compute project. A lot of things were happening around how you deal with the cooling requirements for all the devices we've talked about building. Perkins Liu is going to be back on to discuss all of that. I hope you'll join us then, because there is always something next in tech.